Good morning and good afternoon, and thank you for joining us for today's webinar. I'm Mark Korzenecki with Xylem's Wastewater Ion Exchange team, and with me today is Chris Riley, and he's also with our Wastewater IX team, but he's our technical director. He'll be presenting the bulk of the presentation as we get started. Today we'll be talking about the wastewater recovery and recycling options that are available in the aerospace industry. The emphasis on that is going to be on how smart or digital technologies can be used in these processes. And just before we begin, tell you a little bit about both Chris and myself. I'm one of our senior business developers with our Wastewater Ion Exchange team, and have been with Xylem and our predecessor companies for about 20 years. I'm based in Pensacola, Florida, and I assist our regional sales team in the Southeast and some other parts of the country in evaluating a customer's application and in generally promoting our wastewater ion exchange services. Chris Riley is our technical director. In his role, he oversees the technical activities and research for our wastewater ion exchange services, both in a customer-facing way and also, in a support role too. All right, we've got three basic goals that we like to accomplish in today's presentation and today's webinar. So we'll go ahead and start with reviewing wastewaters that are typically produced in aerospace and defense processes and applications. Then we'll go to reviewing the commonly applied wastewater recovery, recycling, treatment technologies. So kind of focusing on the sustainability aspect there. And then finally, we'll discuss a digital enhancement of wastewater ion exchange by using these remote connectivity tools that we have available. Okay, and a little bit more as far as in depth what we're going to talk about our agenda. Besides helping Xylem and our customers with wastewater applications, I just wanted to say, Chris and I, one of our big hobbies is aviation and aerospace. So I'm thankful I'm based in Pensacola, home of the U.S. Navy's flight demonstration team, the Blue Angels. So that's why we have a picture of that there too. So this topic today is both dear to my heart and Chris's heart, both personally and professionally. So planes aviation is our part of our life. So we're going to talk today. We're going to introduce Xylem and Evoqua. We're going to go and talk about where the wastewater is generated in the aerospace and defense industries. Going to go into the recycling options for wastewater treatment recovery. And from there, go to the digital connectivity platforms. And from there, get a little deeper and talk about a few case studies and how we can implement these technologies and apply the digital aspect to it too. And then finally wrap it up with a summary. Okay, Xylem and Evoqua. Who is Xylem, and what can we offer you? How can we help you with your water needs? So back in May of 2023, Xylem purchased Evoqua Water Technologies, and that's a company that both Chris and I came from. And this included our wastewater ion exchange services. So with that combination, with that merger of the companies, Xylem now has about 20,000 employees worldwide, and we provide water and wastewater treatment solutions, and that's both services and from an equipment standpoint to all these different sectors which are listed. From what we're talking about today, from the aerospace and defense side, all the way through microelectronics to power to healthcare. Really, any sector that has water needs, Xylem plus and Evoqua are going to be able to help you. Our water treatment capabilities fall into three broad categories, which are listed here on the bottom. That's utilities, industrial, and buildings. I won't list all these capabilities in depth, but from a high level, Xylem is able to provide water treatment solutions, from the start of the process, treating an incoming water source to increase its purity, remove contaminants. Then from there, convey the water throughout the process, and then be able to treat the water at the end of a process, either for environmental compliance purposes or for water recovery. And each of those lines there, each of those bullet points just talks about the different types of specific technologies that we can apply through Xylem. Okay, and I will turn this over to Chris to get into the meat of the presentation from there. Thank you, Chris.
Thanks, Mark. Appreciate it. So we want to talk about just some typical processes that generate wastewaters. We could have a whole webinar just on the different processes that are done, within the aerospace and defense realm. We're going to concentrate on several processes that generate wastewater, that use water, consequently dirty it up, and that wastewater then needs to be treated. Metal finishing type processes are processes that you'll find very commonly within the aerospace and defense industry. Those processes can include electroplating, electroplating, anodizing, etching, conversion, coating, things we'll go into in just a little bit more depth in a moment here. In addition to those typical metal finishing type processes, circuit boards are obviously heavily used within the aerospace and defense industries, and the manufacture and or population of those circuit boards is also prevalent within the industry, generates wastewater, and is a target for wastewater treatment. When you're dealing with a lot of metal parts, whether you're doing metal finishing, whether you're forming those parts, whether you're manufacturing them in some certain way, ultimately these parts, whether they be metal, whether they be plastic, whether they be glass, they ultimately need to be cleaned. So cleaning in general and critical cleaning especially are heavily prevalent within the aerospace and defense industries. All right, looking at the metal finishing, which would include, for my purposes, electroplating, electrolysis plating, anodizing, basically those types of processes where you're depositing a metal coating onto a part, or you are affecting a change in the coating on the metal part, in the case of anodizing, for example. Those processes involve a lot of different chemistries and heavy metals. In the aerospace and defense industry, you see a lot of use of cadmium, chromium, copper, nickel, zinc. There's several others as well, but those metals seem to be prevalent in many of these types of different processes. On the plating side, whether it be electroplating or electrolysis plating. The anodizing side, where you're taking aluminum parts and you're actually changing the aluminum coating on the surface for better protection. There's the three different types. One type uses chromic acid for anodizing, and the other types use sulfuric acid typically, or some combination for conversion of this aluminum surface. On the conversion coating side, you see a lot of chromate, which is hexavalent chromium, phosphate conversion coatings, and non-chrome coatings, which are meant to try to replace some of the hex-chrome coatings just because of toxicity concerns and wastewater treatment concerns. In conversion coating, you're just laying a coating across the metal surface, similar to plating, but not exactly like plating. You are putting a coating on top of the surface, which is different from anodizing. A lot of contaminants that you'll generate in these types of processes are more on your heavy and toxic side. You'll have acidity and alkalinity, which is manifested in just higher low pH. A lot of solids. They could be particulate solids, or they could be dissolved solids. Organics, such as oils and greases, other organic compounds that are within the chemistries that are used are also prevalent. I mentioned before some of the metals that are used in plating, for example. So from a contaminant standpoint, a lot of those same metals, cadmium, copper, chrome, some new ones, gold, iron, lead, moly, nickel, silver, zinc, amongst others. Cyanide is another contaminant of concern that can show up mainly from cadmium cyanide plating. There are other cyanide plating processes such as chromium zinc that are also out there. There's decent alternatives for those. Cadmium cyanide itself is a chemistry for which there's not really that many great alternatives, although they do exist out there. Now we're going to talk about circuit board and critical cleaning rinses. That's where you have these assemblies or parts or circuit boards that need some critical cleaning done to them. In other words, what is critical cleaning? It means they are cleaned to a high degree to minimize the amount of contaminant or soils that are left on them, contaminants that could actually impair how they operate, cause their useful life to be shortened. Processes that we encounter on the cleaning side, circuit boards, as well as other critical cleaning applications, immersion processes, spray processes, ultrasonic cleaning. And these processes usually are contained either in a batch or inline continuous type of washer, where you'll have almost like a dishwasher in some cases, right? Or a several compartment type washer where you'll have a washing stage and one or more rinse stages. Contaminants that are generated from these would be solids, particulates, dirt, dust, debris, flux residue, things of that nature, and dissolved solids such as dissolved metals, lead, silver, tin, zinc, copper, things of that nature. So when we're thinking about water recovery, we want to understand why we want to do it, as well as just diving right into doing it. Many times, if water recovery processes are done strictly to save money on the water bill, you may end up being disappointed, depending on what part of the country you're in, especially, or what part of the world you're in, especially, depending on water costs and things of that nature. So you really have to think about why do we want to do this? What do we want to do? Big goals of water recovery. You're trying to improve your sustainability profile. There may be a goal from corporate headquarters or from the facility management to cut back or reuse a certain amount of water in your processing. So improving that sustainability profile can be a goal. You're also maybe trying to comply with local water quality restrictions, or not quality restrictions, but volume restrictions, consumption. Your local water folks may say, hey, you could only have so much water for your facility, and if you're trying to expand or add new processes, then you may run into a bottleneck where you can't get enough water to add those processes. So you need to look at water conservation and or water recovery. If you're looking at compliance considerations, you can have both positive and negative effects of removing wastewaters from your overall wastewater stream that is being discharged. We'll talk about that in a little bit on a couple slides. There's operational considerations. You want to look at the impact of using recovered water on the processes that you're going to use it. If you have a cleaning line, plating line, something like that, and you take that water, recover it, send it back to that line, you have to understand if there are any potential contaminants that could be coming back in the recovered water. Might those affect some of your processes? So you have to understand where it's going, as well as what you want to take out and how clean you want to get it. How clean is clean? You have to understand, or you want to look at the effect of manpower requirements. And you also want to look at centralized systems versus point of use. Do you want a number of systems at point of use locations, or could you consolidate into a centralized system that can feed out to the various points of use? And then again, there's cost considerations, of course, capital costs versus operational costs for these types of systems. So when we're looking to proceed, so we want to think about what are we going to do? So we're looking at doing some wastewater recovery. We want to identify any drivers and constraints. What are the priorities? It goes back to what I just talked about. What are the goals? What are the reasons for doing this? Do you have priorities for water or energy, chemical consumption reduction? Do you have any restrictions in money, right? Capital expenditure versus operational cost. And do you have any corporate or facility sustainability objectives that doing this would help you achieve. So you get past that, you say, yeah, we want to look at this further. We want to determine where any water that you recover could be used. In other words, what impact might it have on whatever process it's going back to? So what processes might you be able to use that recovered water back in the exact same process that it came from? We see that most often in other processes within the facility, cooling tower feed, things of that nature could be also another consideration. What then you have to understand, what water quality do you need from this recovered water for those processes? What volumes and flow rates are required for those applications? So you end up doing a water balance, shall we say. Then you take it to the next step and you look at the existing wastewater streams. What processes generate wastewater? What are their volumes and flows? Are they commingled or separated? Segregated? Can you segregate them if required? Sometimes that can make the treatment process much easier. Then you've got these target streams. Now you want to characterize them. You want to look at them, analyze them, determine what are the constituents and background chemistry of each of these. Are there commonalities between these different wastewaters that you could combine them with no issues? Might any of the constituents be problematic for certain processes or potentially jeopardize compliance, for example? From that information, then you're going to develop your solutions. What technologies are appropriate. We're going to talk in a little bit more detail on a couple of them. Do you want to look at point of use or combined recovery or both? Depending on the types of processes, do you need to do bench or pilot scale testing? Typically, we always recommend bench testing, and we do that at our facility in Minnesota. What is the footprint for each required solution? What are the anticipated maintenance needs? What levels of controls, alarms do you want? Do you want to integrate with your building management system? In the end, in goes the solution. Doesn't mean your work's over. Now you look at it and you say, okay, is it delivering the expected results? How can we optimize it? If need be, can we expand it? All right, let's talk a little bit about wastewater treatment and recovery. What options exist, for example, for wastewater recovery. We'll hone in really on, there's a number, we're going to hone in on a couple specifically, or a few. There's ion exchange resins, take out metals and or total dissolved solids, carbon filtration, old as the hills technology, just like ion exchange, can remove organics, total organic carbon. Reverse osmosis, membrane process, can remove total dissolved solids. Good old filtration, whether it be by media, bag, or cartridge, can take out particulates or solids that you don't want to get into your following processes, such as ion exchange, carbon, or reverse osmosis. And ultraviolet light is used to control organics or control bacteria. Talk a little bit about ion exchange and carbon. It's a very, like I said, old as the hills technologies, very common technologies. Ion exchange resins are just really small plastic beads that are functionalized. They are meant to hold on to one ion, and then when you run your wastewater through it, it exchanges the ion it's holding on to, such as acid or hydroxide in this diagram, and exchange that for whatever contaminants are in the stream. So that little diagram indicates copper sulfate going through cation resin and anion resin. The cation resin removes the copper, puts acid back into the water. The anion resin removes the sulfate, puts hydroxide back in the water, and the result is water, purified water. So the resin will remove dissolved ionic contaminants. It'll take metals and other contaminants down to ppb levels. And you can produce some pretty high quality water with ion exchange resins, up to 18.2 meg, or just call it 18 meg. And there you're talking of TDS, total dissolved solids content, of about 0.03 ppm. So pretty darn pure. Carbon adsorption is used really to remove organics. TOC can also be removing oxidation compounds such as chlorine or hydrogen peroxide. And you'll see ion exchange and carbon used both on the front end of processes to clean up water before it's used in the process, and on the back end to clean up water after it's been used in the process. Reverse osmosis is another common technology. It's not as old as the hills, but pretty darn old. It's been around for a while. Uses polymeric membrane. It's basically a physical barrier. It's a separation process. You can see in the diagram up top, your water goes in, you apply pressure, it forces the clean water, if you will, plus a minor amount of constituents through that membrane, and that comes out as your product, or what's shown there as your permeate. The membrane doesn't allow certain things to pass. The majority of your contaminants, for the most part, will not pass through that membrane, and those concentrate up in what is called the concentrate or reject stream. Membrane pore size is extremely small on these membranes, such that it can retain ions such as sulfate and chloride and things of that nature. RO will remove, most TDS and other contaminants. It'll take out, typically about 95% of the total dissolved solids. It can take out up to 90% of organic carbon, up to 97% of silica, and virtually all of bacteria. Again, you end up with a clean stream, or the permeate, or the product. It could be 10 microsiemens or even under, depending on the quality of water that's going in. And the thing is, too, you have to remember you do or will have a concentrated or dirty stream, or the reject stream, that may or may not need to be treated. There are other filtration type processes, speaking of membranes, that are used in wastewater. Microfilters, they have a larger pore size. Large is in quotes in this case. It's a pore size of about 0.2 microns. Usually a microfilter is used as a pre-treatment step for reverse osmosis or for ion exchange recovery. Microfilters can be used to replace clarifiers, for example, if you have a conventional precipitation system. On the ultrafiltration side, ultrafilters have membranes that will filter down to about 0.02 microns. They'll remove turbidity, particulates, bacteria, pathogens. You'll see a lot of these in some oil and grease type separation applications. And again, these are usually used with disinfection technologies for water recovery on the potable side. We don't see them as often on the wastewater side, but they can be used and ganged up with other technologies. Filtration and UV or ultraviolet light treatment. Filtration removes the solid particulate contaminants. You can see there you've got cartridge filters. You may be able to use bag filters or media filters, which was shown in those tanks in the upper right corner of that picture, where you actually have material or media equivalent to sand, or perhaps even finer, that filters out particulate contaminants, and then those are removed via backwash. Filtration is important because it keeps those things out of your ion exchange resin, out of your reverse osmosis membrane, out of your carbon adsorption media as well. Those things, ion exchange and carbon, they can work for filtration. You do not want them to, because whatever you put in there is ultimately going to come out the backside and cause problems, if they don't cause problems just by plugging those things up. So filtration ahead of IX or ahead of RO is typically a must. Ultraviolet light, again, there's a couple different wavelengths you can use. That's usually to break down TOC or to break down biological activity. When you do use UV, you usually follow that with a submicron filter. You're trying to get out those very fine particulates or microbes that have now been dealt with through ultraviolet light. So if we're looking at recovery or just wastewater treatment in general, there's some rules of thumbs. Are we looking at media? When I say media, I'm talking carbon or ion exchange resin or something similar. When I talk equipment, I'm talking pH adjust systems, precipitation systems, RO, things of that nature. So usually when you have high metals, high volumes, you're looking at an equipment type solution. When you're talking low concentrations of total dissolved solids, that's where media really shines. You're looking at pH or suspended solids, like I mentioned, you're talking equipment type solutions. There are Benefits, pros and cons, obviously, of any type of technology. Media, which we are focusing on really in this presentation. Media solutions typically have lower operator attention. Operator needs to interact with them, so it's usually a lower attention required, lower upfront expense when you're talking media type solutions, and usually a smaller footprint. Doesn't mean media is the solution for everything. Equipment, it has its place, and oftentimes you've got a blend of equipment and media together to make the right solution. When it comes to dilute waste streams, however, media, ion exchange, and carbon are usually the best solution. All right, let's just look at a quick ion exchange treatment example. A very simple process there is it's a wash and a rinse. It's a process chemical and a rinse. When you're looking at an electroplating line, as any of you that deal with that know, your line is just multiples of what we show here right on the screen. Chemical plus a rinse step. So in this case, you've got wash and a rinse. Here's where you would employ wastewater ion exchange. You can do that either for recovery of that water back to the process or discharge treatment if you need to do that as well for discharge to your local wastewater folks who will receive that wastewater and treat it further. When we look at ion exchange on the back end, you really need to make sure you're doing upfront water treatment as well. And upfront water treatment is common in so many different processes, especially in aerospace and defense, where you need a higher quality of water to be used in that wash process, in that rinse process. So here we just show a typical ion exchange makeup DI water system, and then a system on the back end to treat for either recovery or for discharge. You would employ reverse osmosis similarly. Again, you've got to remember with a reverse osmosis, you do have the permeate or product stream the clean stream that you would use back in your process, and you do have a discharge stream. Depending on the type of water quality you need, as we talked about several slides ago, where you need to understand what type of water quality you need going back into that rinse. Typically, whatever water quality your makeup system is producing, that's usually what you're going to want to see on the back end. Or that may be specified by a mil spec or something like that. So if you have reverse osmosis, like I said before, maybe you're making 10 microsiemens water as your product. If you need to clean that further or make that even more pure, that's where you can install a wastewater ion exchange system. We can, of course, forget about the discharge. I mentioned before, there's considerations where you have to understand, if I'm putting in a process, what are all the outputs going to be? If there are metals going in that concentrate up that are now over your discharge limit, well, you might have to remove them. And you could use ion exchange or a media type process for that. Or you might end up with both things. So as you can see, there's a lot of different considerations when you're looking at doing recovery, water recovery. There's a lot of different, not necessarily technologies, but iterations of those technologies that you could use to effect water recovery for your waste stream or waste streams if you have a combination, for example. Now let's talk about this digitally enhanced wastewater ion exchange. First off, when I talk wastewater ion exchange, what is it? From our perspective, from Mark's perspective and my perspective, wastewater ion exchange, it's a service where portable ion exchange vessels or adsorptive media such as carbon or other media are supplied for treatment. These vessels are leased. They go onto customer's site. Customer uses them. When they are spent, they are removed from site and regenerated or rebedded off site back in our Minnesota facility. So wastewater ion exchange itself is this service-based system that uses leased media tanks. Again, from our comparisons before, ion exchange or media type treatment does tend to minimize system footprint. In this particular case, you're eliminating any on-site handling or regeneration. Doesn't mean you can't use ion exchange on-site and regenerate it on-site. You certainly can. This is just a different iteration of that type of process. It eliminates that type of on-site handling. The media, when it does go off-site for handling, it goes to a RECRA permitted facility. Sorry, that facility has all the necessary permits, knowledge, and expertise to handle things appropriately, handle the spent resin, as well as handle the metals that come from that resin, because those metals ultimately end up getting recovered. So, Water One WX services. When we're talking digitally enhanced wastewater ion exchange, that's what we're talking. Talking this service called Water One WX. It combines that wastewater ion exchange service with remote monitoring capability, with data logging capability for those reuse and recycle type systems. Again, ion exchange in general targets lower TDS waters, and in this case, that's highly appropriate for this type of product as well. So what this service does, it provides for that continuous, consistent recovered water quality that's monitored 24/7, 365 days a year by the Digital Command Center. The system will alert for water quality excursions, other things as well, such as high pressure, such as from filter obstructions, leaks, things of that nature. This service basically provides a streamlined operation. For example, when you're running a wastewater ion exchange system or any ion exchange system, you need to understand when your tanks are spent. Some folks do that on time. Some folks do that by analyzing what's going in and what's coming out. And some folks do kind of a combination of that. And others will use quality indicators such as quality lights, connectivity meters, resistivity meters. Essentially, in this case, with this technology, Xylem monitors the system when it says through the alarm trigger for water quality that it's time to change a tank. Xylem arranges for that water, for that tank to be changed through the local branch service network. So that really takes the onus off the customer for having to keep an eye either on the quality light or whatever means of quality measurement is going on. So then those tank changes get scheduled automatically and get affected by the service branch. In addition to just gathering this data, it also stores a lot of this data, which we'll talk about on the next slide. And all this data, or a lot of this data, can then be used or put together in water quality reports that you could use, say, if you have an internal audit or something like that. If you're NADCAP certified, for example, and you have internal audits or audits by external customers, you would have that ability to look at historical water quality data through these reports that are generated. So this system, this unit, what it does is it directly measures and logs feed connectivity, effluent resistivity from, say, if you have a configuration of 1 carbon and 2 mixed beds, which is extremely common, it would monitor the resistivity from both of those mixed beds, monitors the temperature, pressure, loss, pressure differential across the pre-filters, the volume of wastewater processed. So it uses that information also to calculate things such as average flow rate, average feed connectivity, and really through the AI or through the algorithm, it determines how much of that tank is left, essentially, how much of that capacity is left. So it keeps an eye on the system and the amount of capacity that's left in that worker quality tank, just to give an idea of when, for example, the next change may occur. So there's a lot of data that it collects and uses, and a lot of the data shown there, that's an example of the dashboard that you'd typically see. All right, let's talk a few case studies. We're not going to talk all on the digitally enhanced, but just a few different aerospace and defense case studies. Talk conversion, chromate conversion coating. It's one of the most common processes, and this could be, in addition to chromate conversion coating, which is putting down a chrome coating over metal, usually for corrosion protection. This can also extend to chrome electroplating as well as chromate anodizing. or I should say chromic acid anodizing. So this particular case, you had a manufacturer of large aircraft structures. They're doing, we're doing chromate conversion coating on a number of aluminum components because the chromate conversion coating imparts some corrosion resistance and also provides a nice surface for the addition of paint if necessary as well. They were having issues. They're being fined from some contaminant exceedances in the discharge to the city. So we looked at a bunch of different wastewaters. When we look at a particular situation, we don't just usually look at one wastewater unless we know that one wastewater is the problem area. We'll look at a number of wastewaters that could be contributing in our lab in Minnesota. In this case, we identified several rinses, that could be successfully recycled using the just essentially ion exchange resin in this case. Put in a small demonstration system on the recommended rinses. Worked very well, showed that wastewater ion exchange was very effective in meeting treatment and recovery water goals. Went to a larger system then, once that smaller system had proven itself, went to a larger 60 cubic foot vessel system with cation and anion exchange resins, treating up to 150 GPM of those chrome-bearing wastewaters. And ultimately, in the end, they eliminated this wastewater from their discharge stream. They were able then to reduce also incoming water usage because they were using water once through, use it, and then down the drain. In this case, they were using the water, sending it back to the system. So they were able to reduce what was coming in. They eliminated those fines. They improved the quality of the water used to rinse and just made it more consistent. And that it reduced the ultimately rework and any extra labor associated with that. Next, we'll look at a microelectronics manufacturer. They had a smaller ion exchange system. They were looking at trying to optimize this wastewater ion exchange reuse system that is used on some circuit board manufacturing and cleaning wastewaters. In this case, they are needing some high purity water to rinse their circuit boards. So we installed this mixed bed wastewater ion exchange system I mentioned before. Carbon in a couple of mixed beds is our typical configuration, although we're not wedded to that. Whatever configuration needs to go into work is whatever configuration we will specify. In this case, they needed to generate some high quality water. We put in a wastewater ion exchange carbon mixed bed system for deionization, and they needed 16 meg quality back to that process consistently. So ultimately, with some ups and downs with the manual system, mainly just keeping an eye on it, monitoring it. We did install the digital system, the Water One WX system, was connected then to the original wastewater ion exchange system to make it digitally enhanced. And now that system is remotely monitored with those changes scheduled automatically as necessary. So that relieved the customer just of the daily duty of keeping an eye on that system and the quality and making sure that they ordered, replacement tanks as necessary. Now that's all done automatically through that Water One WX system. Some things popped up. We were seeing originally some higher resin usage than expected, and we were able to identify through the historical data that they would have some spikes in conductivity, typically every day, every other day, and turned out ultimately it was a cleaning chemistry that was just essentially getting into the wastewater ion exchange treatment system, causing the tanks to be used more quickly. More TDS you add to those systems, they're in this case, it's a smart system, but the resin itself is pretty dumb. It just takes what you give it. So in this case, these higher spikes led to quicker consumption of the resin. So they were able to get those out of the wastewater ion exchange system, and that helped their tank life, helped extend their tank life, and a little bit of some frustration level as well. And they also have this historical, quality data that they can use for review and or audit purposes. In this case, we were able to use it and troubleshoot. And there's just an example of one of the outputs that you can see from the dashboard of the system. where it shows feed conductivity, it shows the quality coming out of both of the tanks, the worker tank and the polisher mixed bed tank. And it also shows, the flow status. When the system's not running, well, the quality drops because it's really not, there's nothing really flowing through the sensors. When the system's running, as shown by the flow status, then it will register what you see there for effluent qualities. There you can see a few of the little spikes. In this case, they're smaller, but they are still spikes compared to what they normally see. The last case study I want to talk about was cadmium electroplating. Cadmium is used a lot still in the aerospace and defense industries. Cadmium, for all its bad news, all its toxicity, it has some very good qualities when it comes to operation in saline environments, in seawater type environments, just corrosion inhibition, really good lubricity. So you can see cadmium used on a lot of components and fasteners and things of that nature. So cadmium cyanide is still out there and used in a number of processes. In this particular company, it was an aircraft component repair facility. And they were looking to upgrade their conventional system. They had a conventional cyanide destruct system where they would use chlorine bleach to destroy the cyanide and allow the cadmium to be precipitated as cadmium hydroxide metal. So they were looking to upgrade that system. So we were chatting with them about that, but we also said, let's look at that source water. We looked at that source water and determined that the rinse water was actually, other than the cadmium cyanide, it was pretty clean from the respective other contaminants. So we recommended actually Wastewater Ion Exchange to recover that water. So we ended up installing a 30 cubic foot mixed bed wastewater ion exchange system. Removes the cadmium and cyanide as well as any of the other components from the background, generates a consistent water quality of 1 meg, returns it to the process. So in this case, again, they were able to eliminate the discharge of that treated cadmium cyanide water, which also eliminates the potential for oopses from the cadmium cyanide treatment system. They're also able to eliminate the chemicals and labor, that went with that conventional cyanide treatment system. Ultimately, they're getting consistent recovered water quality, and the plus was they did have some sustainability goals for their facilities, so they were able to help those with this particular process. I'm going to turn it back to Mark, and he can summarize.
All right. Well, thank you, Chris. A lot of information there, and what I will do is kind of go through some of the highlights of what you talked about, and then we'll open it up to questions from there. So aerospace and defense operations, there's many different types of wastewaters, and many of those are applicable for recycling or water recovery. So some of the components of that would be wastewaters that have low conductivity, low TDS, equipment and media solutions. How do we determine that? What's going to work best? So we always want to look at, what's the concentration of the metals, and also, how much water is being generated per day in gallons, and we look at those in combination to see how we can recover it and if it can be recovered. And then, as Chris said, there's many different technologies that can either be standalone when we employ that water recovery, or they can be mixed and matched as we have there. Next point, there are a number of things to consider when contemplating wastewater recovery, and some of those are sustainability. A lot of companies these days have sustainability drivers in addition to just from a cost, compliance, and operation standpoint. They want to be able to meet these goals and show that they're good environmental citizens. So that's more and more important these days. But of course, like I mentioned, cost and compliance and operations are right up there with things that go into the mix in the equation. Several technologies or unit operations options exist for wastewater recovery. And as we mentioned, ion exchange and reverse osmosis, the membrane technologies are most common. But then some of the other technologies which go along with that would be, proper prefiltration and also carbon treatment. to remove any organics or cleaners that may be in that rinse water or wastewater. And then finally, the digital connection of ion exchange technologies adds value to a water recovery system. In the aerospace and defense industry, there's very high, high or very, very tight tolerances and specifications which are needed for that water quality. So by having that digital connectivity and to be able to go back and track that and see that historic data, that will help meet a lot of the reporting requirements and historical data retention that's needed to meet those limits, and just to have a good quality part too. And thank you very much for considering Xylem.